Welcome to Lecture 7. Today we're going to look at how ions form. And this should be a shorter lecture looking at oxidations and reductions. So the question is, how do ions form, as it makes more sense for elements to exist as neutral elements? And with that in mind, we're going to ask the question, how do ions form from neutral elements? Okay, that is, we have some atom, put the charge in the upper right-hand corner here. So we have some atom with a 0th charge, and we're going to introduce our chemical reaction arrow showing that it goes to a cation with a plus N charge, or an anion with a minus N charge. Okay, so how does this occur? This is really our question. And the answer is reduction and oxidation reactions. Really, these two things are always coupled. There cannot be an oxidation without a reduction. And so there are many examples or sort of definitions of reduction and oxidation reaction. We'll look at all of them. But to start, we're going to just kind of classify this overall class of reactions as what are called redox reactions or redox processes, where you can kind of see red for reduction and ox for oxidation. And these redox processes are reactions that enable electrons to move to different atoms. Reactions that allow electrons to move to different atoms. Now, a common example would be to take an Na atom, and Na is the atomic symbol for sodium, in case you haven't seen that before. So if we look at our periodic table for sodium, we see that it has 11 protons and 11 electrons in this case, because we have a neutral charge. Now, I haven't defined what the atomic mass is, so we can't look at the number of neutrons, and that's okay. That's not really relevant at this point or for this particular discussion. So sodium 0 is an interesting element. We have sodium, the atom, the element, everywhere, but we don't actually encounter it that often in the 0th oxidation, or excuse me, the 0 charge state. So with a 0 charge state, we don't see that too often because it readily undergoes what's called an oxidation reaction. I'm going to write the word oxidation above the arrow to imply that using some chemical reaction conditions, I'm going to see an oxidation event occur. What's going to happen then is sodium 0, with sodium with a 0 charge, excuse me, is going to turn into sodium with a +1 charge. This would be a sodium +1, and it's an ion, but it's a cation, where we now have an imbalance. Before, we had an equal number of protons and electrons. We would say we had a balance of protons and electrons. Now we have an imbalance of protons and electrons. And without going through the equation, suffice it to say that the proton count doesn't change. And for us to now have an imbalance such that we have a positive charge, we have lost an electron, and we are at 10 electrons. And again, we could use that, we could determine that using the equation that we talked about last time. So we've lost 1 electron. Now the conservation of matter and energy says that we cannot create or destroy matter, we can only transfer it to different states. And so what we need to do is account for that lost electron on the right side of our chemical reaction equation. If you look, the number of protons, the number of protons and electrons on both sides is now equivalent if I have a one electron. Now what this means is there's one electron is formed as a product. This is what an oxidation is. An oxidation is a process where we take one element and we convert it into something that has lost an electron, or maybe more electrons. Conversely, what we could do is we could take another element. This is going to be a Cl, so this is chlorine, 0 charge. Chlorine with a 0 charge has, if we look, 17 protons, because chlorine always has 17 protons. And with a 0 charge, we have a balance of protons and electrons. So we have a balanced number of 17 electrons. And what I'm going to do is just move this whole thing up. There we go. So we don't run out of space on our paper here. Okay, so we have chlorine 0. What I'm going to do with it is I'm going to add to it 1 electron. And I could leave the 1 out. I often write it. It's my force of habit. But I'm going to add 1 electron to that chlorine. And when I add 1 electron to an element, I'm going to get a new chlorine element that has absorbed that electron. So now it's chlorine with 17 protons, because a chlorine atom must always have 17 protons. According to our periodic table, it's atomic number 17. The number of electrons has changed, though. We've now gained 1 electron, and we're at 18 electrons. Gained an electron. And as a result, we now have a charge of -1. This is a new chemical process, whereas before we were looking at oxidations, we are now looking at reductions. And reductions give rise to anions. Okay, so there's a general table that we can see kind of forming here that's helpful to keep in mind. And what I'm going to do is write the table this way. I'm going to have oxidation along the top and reduction along the top. Give myself plenty of space here. What we can do for an oxidation is we're going to remove electrons from atoms. And in reductions, we are going to put electrons into atoms, or atoms will gain electrons. Maybe for parallelism, I'll change the word remove to lose. Don't feel like you need to change your notes. It's not that big of a change. Now, I said there were multiple definitions. They all really stem from this same meaning of removing and adding electrons. They just, the way the electrons are transferred, come in sort of different forms. And so another way to think about oxidation is to add oxygens. And again, I should do some parallelism here. So we are going to gain oxygen atoms. And the reduction is to lose oxygen atoms. And so it's this second definition where we see the term oxidation come from, as oxygen itself is known to promote a lot of oxidation processes, particularly in nature. And there's a third definition I want us to keep in mind, and that is results from the hydrogen count. So in oxidation processes, you can also lose hydrogen atoms, whereas reductions would gain hydrogen atoms. So in each of these three definitions, one involving pure electrons, the other one involving oxygen atoms, and the third one involving hydrogen atoms, we see that oxidation and reductions are opposite in each case. But how the oxidation and reduction process is impacted under each of these definitions is different in each case. So there's sort of a bit of memorizing that we have to do when we're learning oxidations and reductions this way. What I want to just finish up with is looking at salt formations. This is going to be salt formation following redox reactions. Now we said that what we can do is sodium, we could take sodium 0 and let it lose an electron in an oxidation process to give sodium +1. Let's remind ourselves of that. So sodium 0 can undergo an oxidation reaction to make sodium plus. And we balance that reaction by showing 1 electron. And we call that an oxidation reaction. I'm going to abbreviate oxidation as ox. We can also take chlorine 0. And chlorine is not willing to give up an electron. It's willing to absorb an electron. In what's called a reduction reaction, which I'll abbreviate as red, to give us chlorine negative. Now what we can do is mix these two, what are called half reactions, to show an overall redox process. So we could take Na0 plus Cl0, mix them together to make Na plus Cl minus, and we're mixing both of these processes together to give an overall redox process, which shows the transferring of 1 electron. It kind of migrates over from the sodium to the chlorine atom to give a sodium cation and a chlorine anion. And when we have anions and cations, they often combine or bond to each other by way of an ionic bond to form what's called a salt, NaCl. These are bonded through an ionic bond to form a salt. And you might recognize sodium chloride, or NaCl, as common table salt. Okay, so it's a bit of a whirlwind into redox processes. We're going to look at a lot more redox processes in structures and reactivity, and actually that's with a different instructor, so I won't come along for the ride, I guess, sadly. But redox processes are important, and understanding them allows us to understand how various types of salts are formed. Now, I know I went through the terms ionic bond and salt very quickly at the end of this lecture. We're not really going to touch on ionic bonds too much in this class, so I didn't want to spend too much time now. We'll brush up on the definition a little bit when we look at covalent bonds, but the bigger focus of the course will be covalent bonding and forming molecules as opposed to ionic bonding and forming salts. But looking at redox processes allows us to see how ions could form, how anions and cations are actually made from neutral elements.